you start it?
Yeah.
How come it's not telling me? Oh, I guess once they've told you once, that's enough.
Okay. Welcome back to this conference, and we're happy to have Gabe Frieden now talk about crystal invariance theory. The previous talk was actually called differently. It was Introduction to Geometric Crystals. Gabe, you have the scene.
Okay. Well, thank you, Dari and Tom, for organizing this conference and inviting me to speak, and also Pasha to speak so that we can do it. I've given this talk before where I basically was trying to give Pasha's talk and talk about our work at the same time, and I'm excited to be able to have that already taken. Hopefully everyone has some baseline understanding of crystals and a little bit about geometric crystals. So although hopefully, yeah, feel free to ask questions about these things, because if you haven't seen them before, it's definitely hard to digest them in just 40 minutes. Okay, so I'm going to start by just drawing a diamond of 8 subfields of a certain field of rational functions, and this is going to kind of be the organizing principle for the talk. And then I'm going to say more about geometric crystals and geometric RSK, but I'll talk about how you can get those types of formulas that Pasha was writing via matrices and determinants. And then finally, I'll talk about a generalization of symmetric functions that was introduced by Lamb and Pylyavskyy that they call loop symmetric functions. And these are the setting in which the invariants of the geometric crystals and geometric R matrices live. Okay, so here the setting is I'm going to work with the space of M by N matrices with complex entries, and so the so the notation is that for a matrix X, I'm going to denote the ith row by X sub I and the jth column by X super J. And then it'll be convenient sometimes to talk about the products of the elements in a row and the products of the elements in a column, which I'll call pi lower I and pi upper J. Okay, so the geometric crystal operators are rational actions on the, so you take a complex number C and you act on an M by N matrix, and it gives you another M by N matrix. So in Pasha's talk, he was focusing on the case of just single columns, and then also he was looking at 2-column matrices. But in general, we can take any M by N matrix and view this as being a tensor product. So sort of this is the geometric analog of a tensor product of a bunch of 1-row crystals. And one thing that we'll keep doing in this talk is going back and forth between thinking of the matrix as being the tensor product of its columns or the tensor product of its rows. And so when we think of it as being the tensor product of its columns, then the tableau have entries between 1 and m, so we get a GLm geometric crystal structure where the ith operator acts on rows I and I plus 1. But we can also view the matrix as a tensor product of its rows, which are GLn objects, and then we have an action of GLn geometric crystal operators acting on adjacent columns. So this was the example that Pasha used in his talk of the GLm crystal operator E1, which acts on rows 1 and 2. So okay, and because I'm going to be talking about both sets of operators, I'll always use a bar for the maps that act on columns that are associated to GLn, and no bar for the maps that act on rows. Okay, so now Pasha described what these R matrices are, and he described it in a way that seemed to be maybe unrelated to the crystal operators, but it turns out that the R matrices are actually a special case of the crystal operators. So the way this works is that when you have a crystal, you have crystal reflection operators. So Pasha was drawing these strings where you start somewhere and you can apply the crystal operator EI a certain number of times, and then eventually you get stuck and can't apply it anymore. So you can consider the operator that looks at where you are in your I string and just reflects your position. And it turns out that this is an action of the symmetric group on the crystal. So these generate an action of the symmetric group on the crystal. So if you have a GLM crystal, you have an SM action. And it looks like we have, Dari says pi I is the product of the row I. Maybe I'll, yeah. So pi I is the product of the things in row I. That's right. Yeah, and I'm gonna say, okay. So, right. Okay. So you have these crystal reflection operators acting on any crystal, and it turns out that the geometric crystal operators, you can also define a geometric crystal reflection operator, which gives you an SM action. So it turns out that the crystal operators on the GLM crystal operators on rows give you these geometric R matrices which act on rows, which switch the rows. So Pasha was actually talking about the geometric R matrices that switch the columns. And it turns out that these come from the GLn geometric crystal operators acting on the columns. But the upshot basically is that if you specialize the value of C correctly, you get these rational maps acting on adjacent rows or adjacent columns, and these maps generate an SM action, and these maps generate an SN action. So this is the setting. These are the maps that we want to study the invariance of. Okay, so right. So now when we talk about invariance, we actually want to be thinking about these maps rather than acting on the space of matrices. We think of them as acting as automorphisms of the field of rational functions in this M by N matrix of variables. And I'm going to let inv sub R be the subfield of fixed points of all of the Ri, and similarly for inv E, inv R bar, and inv E bar. So we end up with the following picture of subfields. So these are actually all of the possible subfields you can get, because every E invariant is automatically an R invariant because Ri is a special case of EI. So these are the 8 different subfields that you can get, and this is kind of the organizing principle for our work, is we wanted to understand these subfields as well as we could. So, for instance, we wanted to we would like to find minimal generating sets for each subfield, and really the original motivation was that there are various. I'm sorry, I'm having trouble with the video here. Okay, so the motivation is that there's various interesting functions. So Pasha talked about this energy function, or there's also the co-charge of a tableau, which is a function that maybe some of you have seen that is related to the Hall-Littlewood polynomials. And these functions are invariant under various families of these operators. So there should be some geometric lift, a nice sort of the correct, you know, if we, as Sam Hopkins said, there's this art of finding a good detropicalization. And if we find a good detropicalization, it ought to live in the subfield, which is invariant under the operators that the combinatorial function is invariant under. So we originally were trying to study these functions, and we kind of ended up expanding into this whole diamond. And we'll see that the RSK P tableau is invariant under the GLM crystal operators, and the Q tableau is invariant under the GLN crystal operators. And the shape, the common shape, is invariant under both sets. So we'll see that RSK and its geometric analog play a very important role in this story. Okay, so okay, so are there any questions so far? Okay. So now I'm going to go back to geometric crystals and I'll talk about the geometric version of RSK from a different perspective than the one that Pasha used. Okay, so this slide, I decided to call it geometric crystals while standing on one leg. And if we were in person, I would try to do this actually while standing on one leg. But the idea is that this is really the heart of Berenstein and Kazhdan's construction of geometric crystals. So here's the idea. So you start with the Borel subgroup of a reductive group. So in our case, it's just the lower triangular matrices in GLm. And we define rational maps, rational actions of C star on the lower Borel by multiplying on the left by a Chevrolet generator and multiplying on the right by another Chevrolet generator. So this means this is the matrix that is the identity with an A just above the diagonal in one position. And what it does to the matrix is it adds some multiple of row I plus 1 to row I. And then this adds some multiple of column I to column I plus 1. And these entries are calibrated in such a way that the result is still going to be lower triangular. So you create, when you multiply on the left, you create something that's not lower triangular anymore, but then you cancel that out when you multiply on the right. So this is some map that you can define on the lower Borel subgroup, and it has a sort of straightforward generalization to any reductive group. And this turns out to be the correct analog of this turns out to be the sort of correct analog of the crystal operators in the geometric setting. And what that means is that these maps satisfy certain nice axioms. So one thing is that they actually define an action. So it's not immediately clear that this is an action of the multiplicative group C star, but it is. It is immediately clear that these things commute with each other if I and J are far apart. And then the really interesting one is that they satisfy this, EI and EI plus 1 satisfy this sort of colored version of the braid relation, where you have these parameters C1 and C2 that get slightly mixed up when you do the braid relation. And also, these operators have a simple effect on the diagonal entries of the matrix. So they just multiply the ith diagonal entry by C and the I plus first by C inverse. So these four properties are what Berenstein and Kazhdan, they define a geometric crystal basically to be a set of rational actions like this satisfying these four axioms. And the point is that from these four axioms, it follows that if you put this exact parameter into the crystal operator, this will generate a rational action of the symmetric of the Weil group, which is in this case the symmetric group Sm. So they were originally interested in trying to construct by rational actions of Weil groups, and they came up with this very ingenious way of doing it, which also so this was motivated by, they knew that one way to get actions of Weil groups combinatorially was when you have a crystal, you can do these reflection operators. So they basically said, well, what if we could detropicalize the whole crystal picture and use that to get birational symmetric group actions? And they basically figured out that these were exactly the axioms that you need to ensure that you get a Weil group action. Okay, so it is probably not at all clear what this has to do with the sort of down-to-earth geometric crystal operators that Pasha was talking about. And now that's what I want to try to explain in the next few slides. Okay, so as in Pasha's talk, we represent a one-row tableau with entries. So he was using entries less than or equal to n. Here I'm using entries less than or equal to m. But the point is that we just record. So xi is just the number of I, or xj is the number of j's in the tableau. And now we do this geometric look where instead of taking non-negative integer m tuples, we take tuples of complex numbers. And we think of this as being a quote unquote geometric row. And we associate to it a certain lower triangular matrix. So we just put the x's on the main diagonal, and then we put ones just beneath the diagonal and zeros everywhere else. Okay, and this turns out to be the right matrix to use as we'll see. So then when we have our matrix, we associate, so this is going to be an m by m lower triangular matrix, and we just take the product. So x1 is the first column of the matrix. We just take one of these matrices for each column and take their product. And now the proposition that goes back to Yamada is that if I first apply the geometric crystal operator, coming from that tensor product rule that Pasha described, and then I apply this M map, it commutes with first taking M and then doing that geometric crystal operator from the previous slide where you're acting on the left and the right by Chevalier generators. So in a sense, this is telling you that these sort of complicated formulas that describe this action can actually be viewed as in sort of a very natural way as coming from just multiplication in the group GLM. Okay, any questions about that? Okay, so now I've told you what the geometric analog of a one-row tableau is, and I want to tell you what the geometric analog of an arbitrary tableau is. So for this, we're going to use a different, sort of an equivalent way of thinking about semi-standard tableau, which is Gelfand-Tsetlin patterns. So, okay, so a Gelfand-Tsetlin pattern is a triangular array of non-negative integers that is weakly increasing in this direction and in this direction. So GT patterns with M rows like this are in bijection with semi-standard tableau with entries at most M. So probably it's better to just look at this example. So here, this row has 2 1s in it, 1 2, 0 3s, and 3 4s. And so I've done that for each row. And then what the Gelfand-Tsetlin pattern does is it instead of recording these numbers, it records the sort of cumulative sum. So the first entry is 2, the sum of the first 2 is 3, the sum of the first 3 is 3, and the sum of all of these is 6. And then because there can't be any 1s in the second row, we just don't, there would always be a 0 here, 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 here. So we just don't write those zeros. And this is the bijection. And one thing that's important to remember is that the shape of the tableau, 6 3 1, is the bottom row of the Gelfand-Tsetlin pattern. Okay, so now, just like we did with rows, instead of having these integers satisfying, non-negative integers or integers satisfying some inequalities, we just say let these Zij be any complex numbers. And instead of calling these things GT patterns, I'm just going to call them patterns to try to distinguish them. So we want to associate a matrix, a lower triangular M by M matrix to each pattern. And what we do is we just do a slight modification of those matrices that we associated to rows. So for the first row, we so remember that like in the first row, Z11 is the number of 1s, Z12 minus Z1 is the number of 2s, and Z13 minus Z12 is the number of 3s. So we detropicalize minus into division, and that's going to be our factor corresponding to the first row. For the second and third row, we do almost the same thing, except that we kind of do a truncated version where we put just ones on the diagonal corresponding to the part where there couldn't have been any ones in the second row and there couldn't have been any ones and twos in the third row. Okay, so this is the matrix that we associate to a tableau. And so this is just an aside, but basically the way that I like to think about these matrices is that they come from planar networks, so you can use the LGB lemma to compute their minors, and in particular, all of their minors are subtraction free. Okay. Now the point, or one nice thing about this map is that it's a birational isomorphism, and the inverse is very nice. So if we have a lower triangular matrix and we want to recover the Gelfand-Tsetlin pattern, or the geometric pattern that gave it to us, we just take ratios of left justified minors. So for instance, you could check here if you wanted that delta. So delta 2, 3 is this 2 by 2 minor. So if you take that 2 by 2 minor and divide by this 1 by 1 minor, you should get Z23, which is the entry there. So it's birational because sometimes these minors are undefined. So you can't, this is undefined if the denominators vanish, but it's defined for most matrices. Okay, and now we can define the geometric crystal operators on Gelfand on patterns. So what we do is we take our pattern, we form this matrix, we do the geometric crystal operators on matrices. That means where we act by Chevalier generators on either side, and then we take these ratios of minors. And this gives us geometric crystal operators on Gelfand-Tsetlin patterns. And it automatically satisfies the geometric crystal axioms because it is really just coming from these geometric crystal operators on matrices that Berenstein and Kazhdan have proved satisfy the geometric crystal axioms. Okay, and then you can also show that this actually tropicalizes to a formula for the crystal operators on Tableaux or Gelfand-Tsetlin patterns. So we worked this out explicitly in our we have 2 papers, and in the first one we kind of explicitly worked out using the LGV lemma that you really do get a description of the usual crystal operators from this formula. Okay. So any questions? So we'll see that this perspective of geometric crystals in terms of matrices is kind of essential to studying the invariants. And so the next ingredient that we need, let me plug this in. The next ingredient that we're going to need is geometric RSK. So let me first just do a little reminder of what RSK is. So RSK is a bijection from m by n matrices to pairs of semi-standard tableaux of the same shape, where the first tableau has entries less than or equal to m, and the second has entries less than or equal to n. So the P tableau, or the insertion tableau, as it's usually called, is obtained by inserting the rows starting with the top row. So the top row corresponds to 1, 2, 2, 3. The second row is 1, 1, 1, 1, 2. So if I do Schoenstedt insertion, if you don't know what that is, don't worry about it. But if you do, I'm just inserting 1, 1, 1, 1, 2 into this row, and I obtain this 2-row tableau, which then has this Gelfand-Tsetlin pattern. The Q tableau records the shape after each step. So after I had just put the first row in, I had a 1-row tableau of length 4. And after I put the second row in, the new boxes that were added are these. So this is the Gelfand-Tsetlin pattern corresponding to the recording tableau. And so one of the main properties of this map is that although the P and the Q have the description of how you get P and Q seems highly non-symmetric, it turns out that actually if I transpose the matrix and sort of insert the columns instead of inserting the rows, I actually just switch the P and Q. And the other thing about RSK is that it's an isomorphism of crystals. So I have crystal operators on the rows and crystal operators on the columns, and the crystal operators on the rows correspond to crystal operators on the Q tableau and don't affect the P tableau, and vice versa for the GLN operators on the columns. Okay, so it turns out that there's a geometric lift of RSK that has all of these same properties. So so the way that this is usually sort of maybe the most compact way to say this is that geometric RSK is just a birational automorphism of matrices. So the input matrix, we view it as either this, we're thinking of it, as the geometric analog of a tensor product of its rows or of its columns. The output matrix, we're thinking of it as being two Gelfand-Tsetlin patterns that have been glued along their common shape. And this is why it's important that I don't include anything down here. So because I only have two rows, I can't possibly end up with something in the third row. So combinatorially, I could just put a 0 here. But geometrically, the right thing to do is to actually just leave this out entirely. I don't want to put like a 1 or something. I really just need to leave it out, and then I actually have two things that glue together into a matrix of the same size that we started. So, and I'll just say, so our version of geometric RSK that we use is actually tropicalizes to RSK by min plus rather than max plus. It turned out we needed to use a slightly different version in order for it to be an isomorphism of geometric crystals. But these are related by a fairly straightforward transformation. Okay, so now I'm going to explain one way of computing geometric RSK. So given my matrix, we saw this earlier, that the geometric crystal structure on the rows, or the GLm geometric crystal structure, came from forming a matrix for each column and multiplying them together. So I'm going to call that matrix MQ, and I'll call MP the matrix where you do the same thing, but you have an n by n factor for each row. So now geometric RSK, one way to describe it is that it maps X to the pair QP, where Q is, so remember, phi was this map from Gelfand-Tsetlin patterns to lower triangular matrices. And then, so the Q tableau is the inverse of that map applied to this matrix MQ. And P is the inverse of the GLN map applied to this n by n matrix. And I'm sweeping under the rug the fact that if m is not equal to n, you have to actually slightly modify this map, because this map wouldn't be well defined, but I'm just going to ignore that. And so it's not immediately clear that Q and P have the same shape, but it turns out that you can basically view the formation of this product as a geometric analog of row insertion. And then it turns out that the Q pattern here is sort of recording the shapes after each additional row has been added. And so Nomi and Yamada came up with this definition and proved that it works and has all the right properties. It tropicalizes to RSK, it commutes with transposition. So in this formulation, it's clear that it commutes with transposition, but their original formulation was more like the row insertion description I gave of RSK. So, and I'll also mention, so we also use a description due to O'Connell, Tsetlin, and Nikos, where they basically gave a description of geometric RSK in terms of birational toggles. So that's the connection to, that's going to be the only connection to birational toggles. here, but it's a very nice description that it's kind of similar in spirit to the growth diagram description of RSK, and it makes it very clear that the map is invertible and commutes with transposition, and tropicalizes to the description of RSK as essentially a sequence of piecewise linear toggles. Okay. So here is so I'm running short on time, but this is probably, I'll say a little bit about this. So in the 2x3 case, when I form these two matrices MQ and MP, they look like this, and then I take certain ratios of left justified minors, and I get my Q and my P patterns. And one thing that you can observe if you want is that this bottom row actually really is the same for the two in both cases. So here, this delta 2 is just the entry in the bottom corner here, whereas here it's this 2x2 minor, and you can check that this 2x2 minor is really equal to that entry. And so this S1, this first part of the shape, is the ratio of just the product of the diagonal entries, the product of all the entries divided by this S2, which is this polynomial. Okay, so kind of one thing that you might notice is if you sort of squint at this S2 here, if you ignore the superscripts, this looks like an H2 in variables x1 and x2. If you ignore the subscripts and just look at the superscripts, it looks like an E2 in 3 variables. And we'll see that in general, these shape invariants are some sort of generalization of Schur functions in either n sets of variables or m sets of variables. Okay, so basically the setup, everything I've described, if you just work through the definitions, it becomes almost immediate to prove that geometric RSK is an isomorphism of geometric crystals. But now we come to our first main theorem about the invariants. So the idea is if we go back to this matrix here, so these 5 polynomials, it turns out, generate all of the things that are invariant under the GLm geometric crystal operators. So the idea is that the GLm geometric crystal operators only act on the Q pattern. So they don't affect any of these entries. So these things, these 5 polynomials are sort of using this result are easily seen to be invariants. And then the tricky thing is to prove that they generate all the invariants. So we had to use a little bit of algebraic geometry for that. Similarly, the invariants of the GLn geometric crystal operators are generated by those entries of the m by m matrix MQ. And then we also prove as a corollary that the intersection, the things that are simultaneous invariants for both sets of geometric crystal operators are generated by the bottom left justified minors, the ones that are non-trivial. So here there's 3 bottom left justified minors, but this bottom one is just 1. So we just have this S2 and this S1. And here we have S2 and S1. And each of these generating sets is algebraically independent. Okay, so any questions at this point? Okay.
Okay, thanks, Gabe. Let's have another round of applause.
Well, I have a few more minutes. So I mean, I guess maybe what I want to, yeah. So, can I use my last few minutes?
Well, of course, go ahead. Sorry.
Okay. Yeah, I okay. Well, let me just say, so maybe if you've gotten lost at this point, I hope maybe what I'll say in the remaining time is maybe you'll be able to get something out of it anyway. So now this, you can, if you like symmetric functions, then and Schur functions, then you'll probably, I hope you'll like this definition too, which is, so instead of just having m variables and defining the Schur functions as generating functions for those m variables, we sort of think of each row as being n different colors of a single variable. And then what we do is we color the boxes in our tableau along the diagonals. So we color them mod n. And then when we're taking the generating function of these tableaux, whenever we see a 1, we put an x1, but we put the color. So in this case, blue is color 3, green is color 2, and red is color 1. So we get this sort of more refined version of a Schur function. And okay, so then what we do is, so it turns out that these loop Schur functions are the R invariants. This was proved by Pasha Pylyavskyy. So the shape invariants, turns out, are these rectangular loop Schur functions corresponding to rectangular shapes like this. And it turns out that the other generators that we need to generate the R and E bar invariants, what you do is you start with certain columns that I'm not going to say which columns you can put here, but you put some analog of the elementary symmetric function, which is a single column with colors, and then you just kind of attach shape invariants so that the top left corners always have color n, and the bottom right corners always have color m. And it turns out this gives you an invariant, and these actually conjecturally generate this field. So, okay, so kind of this is the final picture that we end up with. So we know that all of these, well, yeah, okay. So I guess I kind of didn't really have a chance to say what this is, but the ring of loop symmetric functions is the ring of R invariants. There's a kind of transpose version that's the ring of R bar invariants. And then everything else is a subfield of one or both of these. And so the ones in black, we're able to prove that they're generating sets, and then these are just conjectural. Okay, so I'll end there.
Questions?
Any questions?
So maybe there's something in the. Oh.
So I have a question, if that's okay.
Yeah.
This coloring of the tableaux, mod n, reminded me of the construction of the n quotient of a partition. Are these somehow related? Can you extract also the n core?
So yeah, so like here, this sequence of shapes here, you're getting from here. Here, let me exit my full screen. So you're getting from this shape to this shape by removing this. Actually, no, that's not what I want to say. Okay, I guess the short answer is not really. Although, yeah, the short answer is I don't really have a connection with n-cores.
Okay, it's fine.
Okay.
Gabriel?
Yeah.
I had a question. Pasha mentioned in his talk this energy functional for.
Yeah.
So what is the interpretation of the energy functional in this upper triangular matrix context?
Okay. So it's okay. So really what you have to do to get the energy is you have to extend your upper triangular matrices. So so here we have an n by n matrix. This is the matrix, that the type of matrix we were looking at before, products of these matrices. But what you actually need to do if you want to understand all of the R invariants is you need to take this sort of periodic infinite extension where you repeat those entries along the main diagonal and put ones along the subdiagonal. And then when you start multiplying these things, so this 2 by 2 matrix is what gave us the RSK tableau, the P or the Q tableau, one of them. But we actually want to sort of record additional information by keeping track of all of this lower stuff. And it turns out that so the loop Schur functions are minors of this big matrix. And one of those happens to tropicalize to the energy function.
When you say minor, finite minors or some kind of
just finite minors.
Okay.
Yeah, just finite minors. So this is yeah. So Lamb and Pylyavskyy proved that if you take a certain loop Schur function of stretched staircase shape, which is some minor of this matrix, you get a formula for the energy function, or a formula that tropicalizes to the energy function.
Thanks.
I've got a stupid question. I know that several people for several reasons have studied loop symmetric functions, in particular those monomials and Schurs. Is there any point of truth for finding results that are known about them? Like I know Dustin Ross had a Murnagana-Nakayama-like rule.
What was your question? Is there any hope of?
Is there any place where where things have been written up? Is there any way of knowing what is known about loop Schur symmetric functions?
Oh, well, so we discussed some of the things in our papers, and actually one of the things we prove is that they really do generate all of the polynomial R invariants. We proved that in an appendix of one of our papers.
But intrinsic property, the rules, little Richardson rules, whatever.
Yeah, so I mean, none of that. Yeah, I mean, this is something I would love to kind of have analogs of Littlewood Richardson or Pierre or something like this for this ring, but none of that is known. Only Murnagana-Nakayama is really known at this point.
Well, is there an interpretation of these loop Schur functions in terms of? I mean, you're saying they're basically determinants, some kind of determinants of these block triplets matrices, right?
Yeah.
So,
exactly.
So is there a way of thinking about them in terms of Fuhrman and Zelevinsky's generalized minors? So you take the generalized minor theory for these infinite block triplets matrices. It should be some affine generalized minor.
Yeah.
And then perhaps somehow there's a way of thinking about them that way.
Yeah. So I've wondered about this.
Because at some point a while ago, I was looking at a kind of chessboard version of your tableau, where instead of you had 3 colors here, I had 2, and
okay,
we had a kind of chessboard Schur polynomial, right? And it was indeed related to the Fuhrman-Zelevinsky generalized minors for type A1 hat. So,
Oh, okay. Oh, that's very interesting. Could you point me to this paper? I would like to take a look at it.
I can send it to you. It's
Yeah,
not published. It's on the archive, but I can send it.
Okay, I would be very curious to look at this, because what has confused me a little bit is that the cluster. So in sort of finite type, when you have just a GLN or something, you can get these cluster algebras where the clusters are certain families of generalized minors.
Yes.
But in the affine setting, it seems like if you wanted to try to do the analogous thing, you get a clustered algebra where the clusters are infinite.
Well, one remedy for that is to, instead of taking the cluster algebra of the whole, unipotent group, which would be infinite dimensional, you would take certain cells of it, which are finite dimensional, and they indeed have, a nice, well-behaved cluster, or at least conjecturally well-behaved cluster structure. They're really finite, and their cluster variables are minors, are of this kind.
Okay, that's yeah. So that's probably the thing to look at. But so I haven't thought about it from that perspective, but it should fit in there. Yeah, that would be interesting to think more about.
If not, I would like as a discussion to add some context, which, by the way, can you all hear me? Because I'm not fully sure. That
I can hear you.
And I'd like to introduce Dari Grinberg, who will be doing the discussion after Gabe Frieden's talk.
Thank you. I'm glad to be here. So because this is all called crystal invariant theory, I mean the name is because it is in a way imitating classical invariant theory, and the imitation is very liberal. It's not clear at all that you can derive one side from the other. So far, I think you cannot do anything like this. You can just be inspired by it. So I wanted to quickly go through the classical results that are in a way similar to some of to this diamond that Gabe has shown. So classically, we have a commutative ring K. We have a space of matrices over K, shape M by N, and you have two actions on it. On the left, you have GLm acting by row operations, and on the right, GLn acts by column operations. And as usual, if a group acts on the space, it also acts on the coordinate ring of the space, which, to be specific, this is the ring of all polynomials in Mn variables. Okay, it sounds muddled. I don't know. I cannot switch microphones, but I could move closer because my microphone would not work, I think. Or, well, maybe it would. I don't know. It's not straightforward. My speakers wouldn't work. Is this better? Okay, good. Oh, the camera even shows me. So the idea is that you introduce Mn indeterminates, you put them in a generic matrix, and you look at the invariance of that matrix, so to speak. The two actions commute, and you can ask for their invariance. You can ask for the invariance of one side, of the other side, and for the polynomials that happen to be invariants under both. So invariance of the product, basically. And of course, GLm has several subgroups. SLM is a symmetric group, upper triangular matrices and lower triangular matrices. And for the sake of completeness, we are working with algebraic groups. So don't worry about the field being too small or the field not being a field. If the field is finite, we are still taking, so basically they have our polynomials to be invariant, they have to be invariant not under what happens to be in GLn K, but also under what happens to be in GLn A for any K algebra A. So this is also known as absolute invariance or algebraic invariance. There's many ways to say it. So if you take the question too literally, you get nothing. If you take invariance under GLm, you just get the constant polynomials because GLm contains scalar matrices. which just scale each monomial by its degree, by lambda to its degree. So it's not being invariant unless the degree is 0. So this is not what we want. So either we restrict ourselves to SLM or SLN, or we replace invariants by covariants, which basically incorporates this knowledge that scalar matrices scale, so they have to scale accordingly. Which means when you act by a matrix G on the polynomial P, it doesn't have to be invariant, it has to be multiplied by the appropriate power of the determinant. At which point you see that the degree has to be a multiple of m and so on. So I believe this is equivalent. It's definitely true when K is a field. So what can we say about SLM invariance? There is a classical theorem here known as the first fundamental theorem for GL or for SL, which is saying that the invariants under SLM, so acting on the left, so invariants under row transformations, are the polynomials in the m by m minors of X, also known as the Plücker coordinates. So these are the minors that use all the rows. If you want invariants under the right, so under the column operations, you have to take the minors that use all the columns. This is basically the same theorem with the matrix flipped. And if you want a polynomial to be invariant under both kinds of operations, you get the only possibility is the determinant, basically. Well, polynomials in the determinant. And if the matrix is not square, there is no determinant, so you only have constants. My favorite proofs of this theorem use the so-called bi-tableau basis. So the obvious basis of the polynomial ring is, of course, all the monomials, but this is not a very good basis to do invariant theory with. So you switch to another basis, which is indexed by pairs of semi-standard tableaus of the same shape. I think you have seen this somewhere. Not the basis, but the pairs of semi-standard tableaus of the same shape. And the elements of the basis are products of minors. The minors are in a way given by the rows of the tableaus, or actually by the columns. So there are several places where you can find this proof. In characteristic 0, you can also cheat your way through via representation theory, but you definitely need bi-tableaus in arbitrary characteristic. Okay, now my preparation for this wasn't as great as I thought it would be. So I thought I would understand this in full. At this point, I have a confidence level of 80% or so of this theorem. It's a more or less theorem, because I figured I thought it through years ago and I never wrote it down. And now I don't fully understand my argument. So what about looking at triangular matrices? Well, so for GL, for SL, you have all the minors that use all the rows. Now you have minors that use the first I rows for some I. And similarly on the right, it's using the first I columns. And if you change lower to upper triangular, you get, instead of the first rows, you have the last rows. And finally, if you want to be invariant under both lower triangular row operations and upper triangular column operations, you get the northwesterly minors, which are the same minors that you know from, for example, Sylvester's theorem on positive definiteness. Those are the minors you have to check if you want to know that a matrix is positive definite. I don't know if there is a deeper connection here. So my impression is that they follow from the bi-tableau basis as well. But as I said, there are some technicalities to be understood. And while everybody knows this, I don't know who has ever written this down. Yeah, I don't know if it's a probability or a p-value. So what about going deeper down the totem pole of subgroups and just going to the symmetric group? A GLn contains an Sn via permutation matrices. So here we are completely out of luck. This is wild stuff. Even if you just have a symmetric group act on one side, you get the so-called multisymmetric polynomials. You can write down pretty large generating sets. I think you cannot write down the syzygies. And even with the generating sets, it's not really clear like which ones are the right ones. This is nowhere like, it's not a polynomial ring at all. It's not clear what to do with this. If you do symmetric groups on both sides, I think it's even harder than that. In a way, this is like the graph isomorphism problem, because if you have the adjacency matrix of a graph, of a directed graph, or of a bipartite graph, actually, that's probably the better option. Then this is the possible isomorphism. This is relabeling the vertices. I don't know whether this is like there is a deeper connection, but it has the feel of a very hard computational problem. Even for m equals n equals 2, when this group is a Klein 4 group, it's kind of tricky-ish, and you don't get a polynomial ring. Finally, if you have the symmetric on one side and the SLN on the other, so this would correspond to R on one side and E bar on the other, then I think the invariants are in a weird isomorphism with the invariants of an n- ary emic. So this is like the classical problem of invariance theory. Sylvester, Cayley, Turnbull, Noether, I think, even have been working on that, and there is like no real answer. People have just been getting further and further cases done. So,
Dari, is that equivalent to trying to take like a GLN irreducible corresponding to a rectangular shape and trying to understand how it decomposes into Speck modules? I feel like it should be related to that.
It might all be related. I don't know. I don't see honestly, I don't see the rectangular Specht yet. But maybe.
It wouldn't be it would be rectangular GLN modules. That's coming from the SLN.
I'm not.
Well, yeah. I probably shouldn't interrupt you with.
Thought about the restriction problem long enough to know the connections. And even here, the isomorphism is actually a linear isomorphism. It's not an algebra isomorphism. So I'm not actually sure whether the difficulty of one problem translates into the difficulty of the other. But like there is so much difficult stuff in the neighborhood of this problem that I feel they're also difficult. And yes, while I give some references, and these notes are on the website, I would happily see some more references. I'm aware of Sturmfelder's book, but I don't think it goes into these deeper things, particularly not into this. Anyone wants to say more? Yeah, I thought Iva was talking about crystals, and so I would be talking about invariants, but in a sense, I'm not really sure of what I'm talking about. Okay, then I think this is the time for Yuri's talk. Is this right?
Can I ask a quick question? I haven't seen these multi-symmetric functions before. Are there multi-quasi-symmetric functions?
They're also known as diagonally symmetric. And yes, there are multi-quasi-symmetric functions too. They're indexed by multi-compositions, and you have all that stuff. And I'm actually working on a paper that uses them a little bit. So yes, they exist.
Okay, thank you.
All right, let's thank Dari.